All right, welcome to the first section of calculus. So we're going to start off talking about limits. And in this section, we're just going to be looking at a very intuitive understanding of limits. We'll give a more precise definition in section 1.4. Okay, but for now, I just want to kind of build up our intuition a little bit as far as limits are concerned. Limits are the building blocks of calculus. So everything you do in calculus is based at its core on the idea of a limit. So let's talk about limits. So first of all, the notation is this, right? So this statement here, that this thing equals L, means that as x gets closer and closer to A, f of x gets closer and closer to L. Okay? This symbol here is read the limit as x approaches A of f of x, right? So the way you read this statement is you would say the limit as x approaches A of f of x equals L. Right? So this is the limit as x approaches A of f of x equals L. Another way that we could write the same thing is we could say that f of x approaches, so this little arrow will read that approaches. We'll say f of x approaches L as x approaches A. Right? So that's another way to write the same thing. So let's, like I said, we'll give a more precise definition in section 1.4, but let's try to wrap our brains around what it is that we're talking about here with limits. So So here I have two functions. Here's f of x, right, and here's g of x. And if we wanted to look, for example, for the limit as x approaches 4 of f of x. So what we're looking for is what function value, what output value are we approaching as x, in other words, the input value, approaches 4. So as x gets closer and closer to 4, what's the output value? So as the input value gets closer and closer to 4, what's the output value? Well, so I'm gonna so 4 is right here, right? So it's this line right here. That's x equals 4. So as I move along the graph of the function toward x equals 4 in this direction as well as in this direction, it looks like the function value that I'm approaching is 5, right? So the limit as x approaches 4 is 5. We would write that like this. We would say limit as x approaches 4 of f of x equals 5, right? Now let's look at part G, because you might think, well, but I mean that's obvious, right? Because f of 4 equals 5, right? So of course the limit as x approaches 4 is 5. But that's not always true. It's not always true that the function value is the same as the limit. So for example, looking at g of x, you'll notice that it's the same exact function, except that now you have this hole at x equals 4, and the function value at x equals 4 is 2, okay? But that's not the limit, right? The limit is still 5, because the value that you're getting closer and closer to as x approaches 4, right? So as x approaches 4, the output that you're getting closer and closer to is 5, right? In this direction, you're getting closer and closer to y equals 5. And from this direction, same thing, you're getting closer and closer to y equals 5 as the input value gets closer and closer to 4. So for g of x, right, limit as x approaches 4 of g of x is also 5, just like it was for f of x. But notice that g of 4 is not equal to 5. G of 4 is 2, right? G of 4 is 2. It's that point right there. So g of 4 is 2. So what this points out to us is that the limit is not always the same as the function value. Okay? The limit is the value that you're getting closer and closer to. It's not necessarily the actual function value itself. Okay? So hopefully this makes that relatively clear. When we're finding limits, one of the approaches that we'll take is to just plug in some values, that get closer and closer to the input value you're looking for, and see what the output is getting closer and closer to. And you can see in this case, we can't just plug in 1, because if we plug in 1, we're going to get square root of 1 is 1, 1 minus 1 is 0. You're going to get 0 in the denominator, and that expression is undefined, right? If you have division by 0 is undefined. So when you plug in 1, this expression is undefined. Nevertheless, it could have a limit. It could be approaching some value. And to figure out if that is the case, and if so, what value it's approaching, then we can make a table of values. Now, it's important when you make a table of values to look at both what's happening as you approach from the left and what's happening as you approach from the right. So what I'm going to do is I'm actually going to make two separate tables, one where I'm approaching from the left and the other where I'm approaching from the right. Okay, so I'm just going to make a little table, x, and then I'm going to call this thing f of x, right? So x, f of x. Now the thing that I need to be getting closer and closer to is 1, right? X needs to be getting closer and closer to 1. If I'm approaching from the left, that means I should be plugging in things slightly less than 1, right? Slightly less than 1. So maybe I could start at plugging in 0, and then maybe I could plug in 0.5, and then maybe 0.9, and then 0.99, right? And I can keep getting closer and closer to 1. I can get as close as I want, as long as I don't plug in 1 itself, because when I plug in 1 itself, the expression is undefined, right? So I'm going to do that from the left. I might come back in and plug in like 0.999 or whatever if it's not clear what's happening. Okay, from the right, I need to be plugging in values slightly bigger than 1. So I might start at like 2, and then go down to 1.5, and then maybe to 1.1, and then maybe to 1.01, and I'm going to try to get closer and closer to 1 from the right as well. So I'm just going to pop these values into my calculator to see what I get. Some of these you could do in your head pretty easily, but it'll go quicker if I just put this in. -1. Okay, so I've got x minus 1 over square root x minus 1. When I plug in 0, of course, I'm just going to get 1. When I plug in 0.5, I get about 1. Well, I'll do 1.70711. If I plug in 0.9, I get about 1.94868. If I plug in 0.99, I get about 1.99499. I'm not exactly sure what's happening yet, so I'm going to go maybe one step further and plug in 0.999. Okay, and when I do that, I get 1.9995. Okay, so it seems like I'm probably getting closer and closer to 2, but let's see what happens when I approach from the right. So I'm going to plug in 2 for x. So if I plug in 2, I get 2.41421. If I plug in 1.5, I get 2.22474. Okay, if I plug in 1.1, I get 2.04881. If I plug in 1.01, I get 2.00499. Let me go one more and do 1.001. Let's see. I get 2.0005. Okay, so it definitely looks like I'm approaching 2 from both directions. So it looks like my output value is approaching 2. So I'm going to say the limit as x approaches 1 of x minus 1 over square root x minus 1. I'm going to guess that this is 2. Right? So I'm going to guess that that limit is 2. Now, I'm going to check my intuition here by looking at a graph. So I'm going to go to Desmos. And if you're not familiar with Desmos, that's okay. Oh, look, there's my family. Oh, that's not what I wanted. I wanted to go to Desmos. So just go to desmos.com and then say graphing calculator. And I want to graph this function, right? So I want to graph f of x equals x minus 1 over square root x minus 1. There we go. So that's the function we get. And now what's happening as we approach 1? So this is 1 right here, right? In fact, yeah, so I can zoom in a little bit so you can see. So it looks like the function value that I'm approaching is 2. Even though the function value itself is not defined at 1, if I can get my mouse right on it. There we go. So you see you have a hole. When x is 1, you have a hole in the graph. But clearly the limit is 2, right? Like the function value that you're approaching, even though the value when x equals 1 is undefined, right? The function value itself is undefined, but you're approaching 2, right? You're approaching 2. So the limit of the function is still is 2, right? And that's pretty clear from the graph. So so there you go. We've verified it, right? So everything's lining up, everything's making sense. So let's do this again with another function. Here's an interesting one, a trig function. Limit as x approaches 0 of sine x over x. By the way, in calculus, whenever we're dealing with trig functions, the values that we plug into the trig function are almost always radians. So you should almost always be in radian mode in your calculator. Okay, so limit as x approaches 0 sine x over x. Well, obviously, right, if we plug in 0, this function value is going to be undefined. We're going to get sine of 0 is 0, and of course 0 is 0. 0 divided by 0 is undefined. It's an undefined quantity. So we can't just plug in 0. But again, maybe this function is approaching some value. Maybe it's getting closer and closer to some value as the input value gets closer and closer to 0. So go ahead and pause the video and give this a shot. See if you can do what we did on the previous page for the previous example, and see if you can figure out what value, if any, what value we're approaching as our input value gets closer and closer to 0. So go ahead and give it a pause. Okay, what you should come up with is you should be getting that this thing gets closer and closer to 1. I think that's the correct answer. But let's take a look at it in Desmos just to verify. So I'm going to do sine x over x. And yeah, notice that as our input value gets closer and closer to 0, our output value should be getting closer and closer to 1. Right, our output value is 1. So even though the function is undefined when x equals 0, the limit as x approaches 0 is 1. Right? So this is the concept of a limit. Right? What you should have done to sort of develop some numerical intuition is you should have done what we did before. You should have made a chart where you're approaching from the left. And so you could have said something like, if I'm approaching from the left of 0, then I might plug in something like, maybe -1, -0.5, -0.9, -0.99. And I don't know what you get when you plug these things in, right? But this is what... Oh, I'm going the wrong way. I'm leading you astray. Sorry, -1, -0.5, -0.1, -0.01, because we need to be getting closer and closer to 0, right? I was getting further and further away. So really, we need to be getting closer and closer to 0. So anyway, but these are things you could plug in from the left, things you could plug in from the right. From the right, you could approach from, 1, and then go down to 0.5, and then go down to 0.1, 0.01, 0.001, right? And you plug these values in here, and you should see that from both directions you're getting closer and closer to 1. Now, one thing that I'll warn you of is that just looking at graphs and making tables of values, I mean, this is a good way for us to develop some intuition, but we can be deceived by this sometimes. For example, we could have a limit that's irrational. So to give you an example of this, limit as x approaches 1 of 3 to the x power minus 3 divided by 5x minus 5. It turns out that this limit is 3 ln of 3 divided by 5. So 3 times the natural log of 3 divided by 5. That's an irrational number. It's approximately equal to 0.6592, but it's irrational, which means it's a non-repeating, non-terminating decimal number. So if you were making a table of values, it would be really hard for you to figure out that the exact limit is, you know, this weird number, 3 times the natural log of 3 divided by 5. So that's one way we could be deceived. Another way we could be deceived is that the limit might not even exist, right? In other words, it's possible that you're not even approaching one value. And a good example of this would be this limit here, limit as x approaches 0 of sine of pi over x. Now, because watch what happens, right? If we make a table, so here I'm just using plus and minuses because it's kind of like the previous example, right? Where if we're approaching 0, we might start at 1 or negative 1 and then move inwards towards 0, plus or minus 0.5, plus or minus 0.1, plus or minus 0.01, and so forth. Well, notice that when you do that, right, when you plug in, let's say you plug in 1 for x, what you're going to get is sine of pi. Well, sine of pi is 0, right? If you plug in negative 1 for x, you're going to get sine of pi divided by negative 1. Well, that's just negative pi, right? Sine of negative pi is also 0. What about when you plug in 0.1? Well, pi divided by 0.1, that's the same thing as 10 pi, right? Right? 1 divided by 0.1 is the same thing as 10. So this would just be 10 pi. Well, any integer multiple of pi, or rather, let me say, sine of any integer multiple of pi is just going to be 0. So 10 pi is 0, negative 10 pi is 0. If you divide by 0.01, that's the same thing as 100 pi. That's going to be 0. This is the same thing as 1,000 pi, right? 10,000 pi. But you're just going to get 0 every time. And so looking at this table, you might think, well, clearly the value that we're approaching is 0. But that's actually not true. And if we take a look at this graph in Desmos, you'll see that that's not true. So let's do that. So we want to look at sine of pi over x. Sine of pi over x. Okay, so look at this nastiness, right? As x approaches 0, this thing just starts to oscillate really quickly. Okay, as x gets smaller and smaller, the period of the sine function shrinks more and more and more, and so it just oscillates really fast. So what I'm going to do is zoom in. I'm going to zoom in, and you can see that this thing is just oscillating more and more quickly. So if you're thinking about, well, what output value are we approaching? I mean, you know that the function is trapped between negative 1 and positive 1, right? So the output values are all trapped between negative 1 and positive 1. But there are infinitely many real numbers between negative 1 and positive 1. So what's the limit? What's the function value it's approaching? Well, limit doesn't exist, right? It's not approaching any single value. It's approaching infinitely many values between negative 1 and positive 1. So the limit doesn't exist. This thing doesn't have a limit. It's kind of a crazy function, right? But anyway, that's what we would say about that. So we would conclude that actually this limit does not exist. DNE stands for does not exist. Okay. Anyway, so the reason I'm giving you these two examples is just to show you that we're going to want to develop some good algebraic techniques for calculating limits. And that's something that we're going to do throughout this semester. We're going to build up all kinds of tools for being able to calculate limits. We'll start doing it in 1.2, right? But for now, in this section, let's just stick with graphs and tables for a little while to help build our understanding a little bit more. So we're just going to stick with tables and graphs and stuff. So let's look at a few more examples. So let's use a table to find a few limits. How many examples do I have? We've got 3 examples, right? So we'll do three more examples of using tables to find limits. So let's do limit as x approaches 2 of 3x squared minus 1. Now, this is one of those cases where if you just directly substitute 2 for x, you're not going to get something that's undefined. And usually when that's the case, the function value that you get is the same thing as the limit. Okay, but let's just make our table anyway to verify that that's true. So what I suspect is that if I plug in 2, I get 2 squared is 4, 4 times 3 is 12, 12 minus 1 is 11. So I suspect that this limit is equal to 11. That's what I suspect, because that's the function value when you plug in 2 for x. But to make sure, to verify that that's true, let's look at a table. So as we approach from the left. So from the left, I need to be plugging in numbers slightly less than 2. So I might start at like 1, and then go up to maybe 1.9, 1.99, 1.999, okay, from the right. From the right, I need to be plugging in numbers slightly bigger than 2. So I might start at, like 3, and then go down to 2.1, and 2.01, and 2.001. And if I need to plug in numbers even closer to 2, then I'll do that. Let's see what we get. So 3 times 1 squared minus 1 is 2. If I plug in 1.9 instead, I get 9.83. If I plug in 1.99, I get 10.8803. And if I plug in 1.999, I get 10.988. So I think it looks like it's getting closer and closer to 11. Let's try from the right. What happens when we approach from the right? So I'm going to plug in 3 for x. Ooh, I get 26. If I plug in 2.1, I get 12.23. If I plug in 2.01, I get 11.1203. And if I plug in 2.001, I get 11.012. So I'm pretty convinced that I'm approaching 11 from both directions, right? So I think that this one checks out. I'm not going to graph this thing in Desmos. This is a parabola, right? It's a parabola. It's been shifted down 1, and it's been stretched by a factor of 3. So the vertex might be here or something, but it's looking something like this. I mean, it's a continuous function. There are no holes or anything like that. So the function value I'm approaching when x is 2 should be, or the output value that I'm approaching as the input value approaches 2 should be the same as the function value itself, right? 11. So that makes sense. But it doesn't always work out, because on this example, if you directly substitute 3, you're going to get 4 over 0, which is undefined, right? Okay, so that doesn't really work out for us very well. So you just have to plug in values. So let's do that. Let's approach from the left. So from the left, I might plug in, 2, and then 2.9, 2.99, 2.999. From the right, from the right, I'm approaching 3 from the right, so I might start at like 4 and then go down, shrink down to like 3.1 and then 3.01, 3.001. So I'm getting closer and closer to 3. Let's see what we get. 2 plus 1 divided by 2 minus 3 equals negative 3. If I replace it with 2.9, by it I mean x, I get negative 39. Ooh, okay, that jumped quite a bit. If I replace x with 2.99, ooh, I get negative 399. That's interesting. If I replace it with 2.999, I get negative 3,999. So I bet I can guess if I replace it with 2.9999, I think you'd get negative 39,999 probably. This is interesting. This is not approaching a finite value. This seems to be exploding down to negative infinity. Well, what happens when we go from the other direction? So if I plug in 4. If I plug in 4, I get 5. What if I plug in 3.1? Well, then I get 41. If I plug in 3.01, I get 401. I'm going to guess this is 4001. Let's see. Let's see if I'm right. Yeah, 4001. Okay, so from the right, it seems like we're exploding off to positive infinity. So this thing looks like it's going to negative infinity from the left and positive infinity from the right. What could that mean? Well, if you've got a graph and we're approaching 3, we're saying that as we approach from the left, this thing is going down to negative infinity. So it's going to go, I don't know exactly what it looks like, but it's going to do something like this. Whereas from the right, it's exploding off to positive infinity, so it must be doing something like that from the right. So you have this kind of vertical asymptote thing. We'll talk about this in a little bit more detail in a second. But for now, to answer the question, what would we say about the limit? Well, we would say the limit does not exist. Okay? The limit does not exist. Which reminds me of Mean Girls. Anyway, but the limit does not exist. Okay? You can get a better picture of this if you graphed this function in Desmos. I'm not going to waste your time showing you that. You can do that on your own if you want. But yeah, that limit definitely does not exist. Well, let's look at part C. There's another example where if you just plug in the input value of negative 1, you're going to get something over 0, which is undefined. So you can't plug in the input value itself. You need to plug in values that are successively closer and closer to that input value to see what output you're approaching. So let's do that. Okay, so from the left, I would need to plug in values slightly less than negative 1, so maybe like negative 2, negative 1.1, negative 1.01, negative 1.001, and I'm going to run out of space, but and then from the right, I need to plug in values slightly bigger than negative 1. So something slightly bigger than 8, so like 0, and then maybe I could go down to like negative 0.9, negative 0.99, negative 0.999. So I'm getting closer and closer to negative 1 from both directions. Now let's see what we get. So I'm going to have negative 2 squared minus 1 divided by negative 2 plus 1. And I get negative 3. If I replace negative 2 with negative 1.1, I get negative 2.1. I'm going to replace x with negative 1.01. I get negative 2.01. Okay, so I think I see what's happening. So negative 2.001. It definitely looks like we're approaching negative 2. But let's see what happens from the right. If I plug in 0, I just get negative 1. If I plug in negative 0.9, we get negative 1.9. We plug in negative 0.99, negative 1.99. Okay, so I'm willing to bet that next one's negative 1.999. So again, looks like we're getting closer and closer to negative 2. So I'm going to say that limit is negative 2. Okay, again, you feel free to graph this thing in Desmos to verify that this is correct. Okay, but that's that. So as we've seen in each of these examples, when we're determining limits, we've always been looking at the value that x is approaching from both directions, right? So for example, consider f of x here. So this is some kind of weird function that has this sort of jump. So it's like we're on this part of the function until we hit x equals negative 2, and then right at x equals negative 2 we suddenly jump up to this top portion and continue onward, right? So as we approach x equals negative 2 from the left, f of x approaches 1. On the other hand, as we approach x equals 2 from the right, f of x approaches 4, right? Since the two sides of f of x approach different values, right? This side is approaching 1, this side is approaching 4. Since the two sides are approaching different values, we say that the limit of f of x as x approaches 2 does not exist. In other words, limit as x approaches 2 of f of x does not exist, right? However, these half limits, these one-sided limits, I guess you could say, they do exist, right? So the limit from the left is 1, and the limit from the right is 4. So here's how we would write this. We would say limit as x approaches 2 from the left, right? When we have a little negative sign as a superscript, that means that we're approaching from the left. When we have a positive sign as a superscript, that means we're approaching from the right. So the limit as we approach 2 from the left is 1, right? The limit as we approach 2 from the right is 4. But the limit as x approaches 2 does not exist, right? So these one-sided limits exist, but the two-sided limit does not exist, right? So let's introduce that vocabulary, right? So this limit, the original limit that we defined on page 1, is called a two-sided limit, whereas these two types of limits are called one-sided limits, okay? So if you're only looking as you approach from the right, or if you're only looking as you approach from the left, then that's a one-sided limit. If you're looking as you approach from both directions, that's called a two-sided limit. And a two-sided limit equals some value if and only if each of the one-sided limits equal that same value, right? So in other words, in order for a two-sided limit to exist, both of the one-sided limits have to exist, and they have to be the same number, okay? They have to be the same number. So like in this case, both of the one-sided limits exist, but they're different numbers, and consequently, the two-sided limit does not exist, okay? So let's practice with this a little bit. So this first example says, explain why the limit as x approaches 0 of absolute value of x over x does not exist. Well, absolute value of x over x. In order to describe this thing, it might be useful to remind ourselves that the absolute value of x has the following piecewise definition. So absolute value of x is just itself if x is greater than or equal to 0, or it's the negative version of itself if x is negative. In other words, right, you know that the absolute value of a number takes that number and makes it positive. So if it's positive, it stays positive. If it's negative, it becomes positive. So imagine that x is 2, right? If x is 2, then x is definitely positive. So absolute value of x is just going to be 2. But now imagine that x is negative 2, right? If x is negative 2, right, x is negative, then the rule that we're going to use is negative x, right? We're going to get negative 2. Well, negative 2 is positive 2, right? So absolute value of negative 2 is positive 2. So that's how this piecewise definition works. If you've never seen it before, this is the piecewise definition. Now here's why this is important then. Because if you're looking at absolute value of x over x, well, that would be positive x over x if x is positive, or it's going to be negative x over x if x is negative. But we can simplify this, right? Because x divided by x is just 1. So this is 1 if x is positive, and negative 1 if x is negative, if x is less than 0. So in other words, if you were thinking about a graph of this function, here's what the graph would look like. So f of x is equal to 1 if x is greater than or equal to 0. Okay, so it's just a horizontal line at 1. Okay, for all of the positive values, for x greater than or equal to 0. For x less than 0, right, so for all the negative values of x, the function value, the output value is going to be negative 1. So we use an open circle there because we're not using the bottom rule when x equals 0. We're only using the bottom rule when x is strictly less than 0. So that's what f of x equals absolute value of x over x looks like, right? It looks like that thing right there. So looking at the graph, it's easy to tell now why the limit doesn't exist, because as you approach x equals 0, as your input value approaches 0, from the left, the output value is approaching negative 1. From the right, the output value is approaching positive 1. Since you're approaching two different values, this limit doesn't exist. So in symbols, we could say this. We could say, well, obviously, limit as x approaches 0 from the left is equal to negative 1, whereas limit as x approaches 0 from the right of this function is equal to positive 1, and therefore limit as x approaches 0, the two-sided limit, does not exist. Okay. Now, instead of doing a graphical interpretation of this, you could have made a chart, right? And so you could have made a table of values. You could have said something like, from the left, I might plug in something like, negative 1, and then negative 0.1, negative 0.01, right? Well, what are you going to get? If you plug in negative 1 to the absolute value, it's going to become a positive 1. Positive 1 divided by negative 1 is negative 1. Positive 0.1 divided by negative 0.1 would be negative 1, right? This one would also be negative 1. That's as you're approaching from the left, right? From the left. As you approach from the right, you'd be plugging in 1, then 0.1, 0.01, and so forth. Well, then you're going to get 1 and 1 and 1 for your output. Your output values are all going to be positive 1. So you can see that you're approaching different values from the left and from the right. You can also plug this function into Desmos to see that it does indeed look like this. And I'm not just making stuff up. But anyway, so that's that one. Here's another example. So let's find some limits. So here we've got this crazy graph. This is some function f, and we're asked to find the limit as x approaches 1. So limit as x approaches 1. So as our input value gets closer and closer to 1, from the left and from the right, it looks like our output value is approaching 1. Okay? What's the limit as x approaches negative 3? Well, from the left and from the right, as our input value gets closer to negative 3, our output value looks like it's getting closer and closer to 5. What about -1 though? As our input value approaches -1, we're approaching two different output values. We're approaching -1 and +1. So what's the limit as x approaches -1 from the left? Well, from the left, it looks like the output value we're approaching is a +1. From the right, it looks like the function value we're approaching, the output value we're approaching is -1. And since you're approaching two different values from the left and from the right, this limit here, the two-sided limit, does not exist. Okay. Well, what are the function values, right? f of 1 is 1. f of -1. Well, notice that you have an open circle here, so that's not the function value, but you have a closed circle down here. So f of -1 should be, it looks like -1. Okay? Okay, let's look at another one, kind of a similar one, but, well, actually, it's almost exactly the same. It's just that we've taken this piece and we've moved it up, right? So let's see what we get now. Limit as x approaches 1. Looks like it's going to be 3, right? As you approach from either direction, the output value you're approaching is 3. -3, as x approaches -3, I think the output value is approaching 5. As x approaches -1 from the left, it looks like the output value is +1. As x approaches -1 from the right, it looks like the output value in this case is again +1. So that tells us that this two-sided limit does exist, right? Because each of the one-sided limits exist and they're the same value. So the two-sided limit exists and it's equal to that same value, 1. What's f of 1 this time? f of 1 is 3. What's f of -1? f of -1, there's a hole there. It doesn't exist. Right? The function value does not exist at -1. Okay, so that's that. We saw an example earlier of a function that shot off to -infinity from the left and +infinity from the right. So that could happen, right? As x approaches some value a, it could be the case that limit as x approaches a of f of x is equal to infinity, or that limit as x approaches a of f of x equals -infinity. Now, in order for these two-sided limits to exist, even if the limit is infinite, they need to be going the same direction, right? So the one-sided limits need to both be approaching +infinity, or they both need to be approaching -infinity. If you have, you know, one of your one-sided limits approaching -infinity and the other one approaching +infinity, then the two-sided limit does not exist. Okay. We'll go through a couple examples, hopefully, to get you to see the difference. So, number 6 says, use numerical evidence to make a conjecture about this limit, and then check the work by looking at a graph. Well, hopefully you know what 1 over x squared looks like graphically, but we'll follow the directions anyway. So, from the left, so we're approaching 0, right? Okay, so from the left, we might plug in -1, and then -0.1, then -0.01, -0.001. And from the right, we might plug in 1, and then 0.1, 0.01, 0.001. And you know what? Since you're squaring the values, I think you're going to get the same outputs here as what you get here, which is nice. Let's see what those outputs are. 1 over -1 squared is 1. That means this is also 1. If we replace it with 0.1, we get 100. 0.01, we get 10,000. And I'm going to guess that this next one is probably 1,000,000. Yep. Okay, so clearly, right, this is shooting off to infinity. They're both shooting off to positive infinity, right? So here we could say, limit as x approaches 0 from the left of 1 over x squared is infinity. Here we could say limit as x approaches 0 from the right of 1 over x squared is positive infinity. Therefore, limit as x approaches 0 of 1 over x squared, the two-sided limit, is also positive infinity. Pretty clearly that's the case, right? By the way, the graph, and you can verify this in Desmos, but the graph looks like this, more or less. Okay, it looks something like that. So obviously you're going off to positive infinity. Let's do the same thing for number 7. We want to take the limit as x approaches pi over 2. Oh, that's kind of nasty. But we want to take the limit as x approaches pi over 2 of tangent x. Again, make sure you're in radian mode in your calculator. Let's do this from the left. And pi over 2 is like 1.5 something, I think. Let me see. Pi over 2 is approximately 1.5708. So if I'm approaching pi over 2 from the left, I might want to plug in something like 1, and then maybe I can do 1.5, and then maybe 1.56, I don't know, 1.57. I can't plug in 1.5708, whatever. I can only go, because I can't plug in pi over 2 itself. But those will be good values from the left. From the right, remember, pi over 2 is about 1.5708. So I might start at like 2, and then go down to, I don't know, maybe 1.6, and then maybe 1.58, or something like that. Maybe down to 1.571. That's still slightly bigger than pi over 2. Let's see what we get. So again, make sure your calculator's in radian mode. But again, I'm going to do tangent of 1. That's about 1.55741. Tangent of 1.5 is about 14.1014. Tangent of 1.56, 92.6205. Tangent of 1.57 is 1,255.77. So I think this one's going off to positive infinity, right? As we approach from the right, so if I plug in tangent of 2, I get negative 2.18504. If I plug in 1.6, I get negative 34.2325. If I plug in 1.58, I get negative 108.649. And if I plug in 1.571, I get negative 4,909.83. So I think this one's shooting off to negative infinity, it seems like. So your two-sided limits, so as you approach from the left, so we could say limit as x approaches pi over 2 from the left of tangent x is equal to positive infinity, whereas limit as x approaches pi over 2 from the right of tangent x is equal to negative infinity. And therefore, the limit as x approaches pi over 2, the two-sided limit, as x approaches pi over 2 of tangent x does not exist. And if you're familiar with the graphs of the trig functions, which you should be, then that makes some sense, right? You know that the tangent function has asymptotes at pi over 2, right? Pi over 2, at negative pi over 2, at 3 pi over 2, and so forth, right? Negative 3 pi over 2, and etc. So this is pi right here in between. But the tangent function looks like this, right? It almost looks like a bunch of cubic functions repeated over and over and over again. Well, so clearly, as you approach from the left, f of x goes to positive infinity. As you approach from the right, f of x goes to negative infinity. Okay? So that limit doesn't exist. One thing that you might kind of be catching on to is that if one of these one-sided limits goes to positive or negative infinity, then the graph of f of x has a vertical asymptote at that value, right? So like in this case, both of our one-sided limits were going to positive infinity as x approached 0. So that meant we had a vertical asymptote at x equals 0. Here, we had our one-sided limits going different directions, one to positive infinity and one to negative infinity as x approaches pi over 2. But that means you have a vertical asymptote at pi over 2, right? So if you have some kind of infinite limit, whether it's one-sided or two-sided, well, that means you have a vertical asymptote at that location. So I just want to give you one more example. This kind of covers everything that we've talked about, I think, in this section. I copied this directly from your book. But anyway, let's go through this and see if we can figure out what all these limits and stuff are. So for part A, we want the limit as x approaches negative 2 from the left. So as our input value approaches negative 2 from the left-hand side, it looks like our output value is approaching positive 1. Okay. As we approach negative 2 from the right, it looks like our output value is approaching negative 2. So those two-sided limits are approaching different values, which means that, those one-sided limits are approaching different values, which means that the two-sided limit doesn't exist, right? Part C asks us for limit as x approaches 0 from the left. So as x approaches 0 from the left, looks like f of x is approaching 0 as well, right? So our output value is approaching 0. What about when we approach 0 from the right? When we approach 0 from the right, it looks like we're shooting down to negative infinity. So this thing, I'm going to say, is negative infinity. Limit as x approaches 4 from the left. This is a tricky one, right? This is one of those oscillating things that starts oscillating quicker and quicker and quicker the closer we get to 4. So as we approach 4 from the left, I'm going to say that limit doesn't exist. As we approach x equals 4 from the right, it looks like that limit is going off to positive infinity. Okay. So those are the answers there. Hopefully that makes some sense to you. Part G is asking us where are the vertical asymptotes. Remember, you have vertical asymptotes wherever you have an infinite limit. So we had an infinite limit when we were approaching 0. That means there's a vertical asymptote at x equals 0. And then we had another infinite limit when x was approaching 4. So that means we've got another vertical asymptote at x equals 4. And you can see that on the graph, right? You've got these vertical asymptotes here and here. Okay. So that's the idea. And that's all I have to say for this section. It's been a long one, I think. Hopefully they're not always this long.